the only one that got a majority vote was that the Big Bang shouldn't be understood as describing a beginning of time. What the Big Bang really is a theory that says the universe was in a very hot, dense state 13.8 billion years ago. That we can be very confident of. What happened before the hot, dense state, that we can't be confident about that. We don't really know.
All right, so welcome everyone to today's interview, where I'm very pleased to welcome Phil Halper and Professor Niayesh Afshordi. Phil is a fellow of the Royal Astronomical Society, a science popularizer, and runs the excellent YouTube channel Phil Halper, aka Skydivephil. Niayesh Afshordi is a professor of physics and astronomy at the University of Waterloo. He is also a founding faculty member of the Waterloo Centre for Astrophysics and associate faculty in the Cosmology and Gravitation group at the Permanent Institute for Theoretical Physics. Anyway, my guests today have co-authored the book Battle of the Big Bang, The New Tales of Our Cosmic Origins. Yeah, there it is right there. I'll include links for where people can find it as well in the description. But that's going to be our focus for today. And feel free to add anything. But with that, welcome and thanks so much for being here, Phil and Niayesh.
Thanks. Great to be on.
It's a pleasure to be here.
Awesome. So Phil, maybe to start, can you talk a bit about what the impetus was for writing this book? Like what led you to collaborate on it?
Yeah, so I had a YouTube series called Before the Big Bang, which featured interviews with like leading cosmologists about what might have triggered the Big Bang. So I'd interviewed a lot of the big names in the field, Stephen Hawking, Roger Penrose, Alan Guth, but one name just kept popping up, and that was Niayesh. I kept seeing his name in like articles in Scientific American and like various papers on the archive, and like, oh, another new model for the Big Bang. Let's have a look at that. So, and then someone else suggested, yeah, you've got to speak to this guy. So I went to interview Niayesh to make some films about his models of the Big Bang, and we hit it off straight away. And the idea is to turn it into a book sort of popped up. And the book is quite different to the film. So if you've seen the YouTube series, it's quite different, but the topic is the same. So what's different is, you know, in the films, you just try to explain the science. But in this, we want to tell stories. So all the sort of stories of the rivalries between the scientists and the real human drama of how science is done and how it unfolds and what it's like to be at the edge of knowledge. So we hit it off. We decided to write the book, and finally it's out.
Yeah, awesome. It's really, really a fascinating book. I didn't have a chance to read the whole thing, but I think I've read enough of it to ask some good questions here. And then, yeah, so Niayesh, could you give maybe a brief overview of the book? What are some of the key issues, and what could someone expect to learn from reading this?
It's great, as I said, to be here. And the story of the book, I think is a fascinating story how it came to be. But yeah, so what we started to do and then what it came out to be, I'm not sure if they're exactly the same. It's certainly had its own journey with many people. I mean, we wrote it, but then of course there were lots of people who influenced what came out, including our editors. But it's really what it is a story of how science works. And we start by kind of going through the history, but it's not really a history book because a lot of the things about the history of how theory of Big Bang from the Greeks to Galileo and Newton to Stephen Hawking to Roger Penrose. So these are all, you can find them in many other books, and like how we decided that there's a Big Bang as opposed to a steady state. These are all kind of preambles to what's to come. We all covered that in our first chapter. What we actually get into, basically from chapter 2 onwards, is the ongoing debates, things that are happening right now. And they have been, I mean, it's not that they just started right now. They started maybe 20 years ago. But these are debates that have been ongoing. And they are very heated, they are very controversial, and very aptly so, because we all care about our origin, right? Everybody cares about where they came from. And I think we highlight in what sense we have made a lot of progress in the past 50 years, or in the past, even more so in the past 20 years, in understanding our origins. But also, in what sense there is a lot that is left to be imagined, because our progress has been limited because it's just a hard problem. And that leaves a lot of room for imagination. That's why there are many ideas. Some are kind of fringe ideas, others are more mainstream. But just because one idea is mainstream and another is fringe doesn't mean that one is more correct than another. And this is another way that kind of our book is different, because we're not pushing anything. I have like six models that I kind of came up with. I try to be democratic to them. I always say it's like your children. You might have a favorite one. You shouldn't say who is the favorite one in words. And of course, there are other models as well that I mean, again, there are other people's models, so maybe not my favorite, but still I try to be fair. And of course, Phil has always been there, so we try to balance things against each other. So even if I had some implicit bias, Phil tried to correct me on those. But at the end, we kind of say that, so there are all these ideas out there, and we have to decide how to make progress. And we kind of decide how much progress can be made. So it's really an optimistic book at the end, because we said this, in spite of all the controversies, there are these concrete steps that can be made to make progress. But then at the same time, we say that there are other places where these battles will be ongoing, because that's part of our humanity. And that's where we're contrasting kind of our scientific battles with religious battles that have been ongoing, and then where they interface, and to what extent models of the Big Bang are similar to creation stories that we've heard from old books, from Old Testament and many other cultures, and to what extent these modern stories are different from those. There are similarities and there are differences. And I think we have to understand both science and religion to be able to kind of understand this contrast.
Yeah, very, very good. Yeah. So yeah, one thing you mentioned there was, well, you cover a little bit of the history, but it's not really a history book. But I did want to ask, Phil, the book subtitle is The New Tales of Our Cosmic Origins. But in a way, some of the battles discussed they've been discussed for millennia, really. So maybe talk a little bit about some of that history there and how it led to today.
I mean, a lot of the ideas, it's a very good point that these ideas go back thousands of years. So some of the basic ideas, do we live in a multiverse? Do we live in a cyclic universe? Did the universe come from nothing? Is it eternal? Is it not? A lot of these ideas have their roots thousands and thousands of years ago. So just to give a few examples of models that we look at in the book. So one, of course, is the multiverse. That's a very popular idea today. And that idea, I think you can trace back to the atomists. They sort of describe something that sounds very similar to a multiverse. I mean, obviously, in the details, they wouldn't have had any of the notions that we have today. But I think in the rough, broad outlines, it's very similar. Similarly, there's a model called the ekpyrotic model, and that name actually comes from the ancient Greek Stoics. So it's a cyclic universe, and of course, the idea of cycles has been around, for thousands and thousands of years, going back at least to the sort of Buddhists and Hindus, and you can find it in Greek philosophy as well. So the idea is sort of universe from nothing. That also has antecedents in ancient philosophy. So some of these ideas are very new and just couldn't have been imagined thousands of years ago. But many of them are quite similar to what the ancient Greeks, the Hindus, the Buddhists, and others have had in mind. So I think our story is a story of battles that have been raging for millennia.
Very good, yeah, for sure. And then when it comes to the Big Bang, maybe we should talk about that a little bit. So yeah, I'll direct this at Niayesh, but of course you can both comment on this. Maybe it's a common conception that according to the Big Bang theory, well, it all started with the Big Bang, right? The universe began from maybe absolute nothingness and expanded and cooled from the hot dense state maybe 13.8 billion years ago, roughly. But you write about how this is maybe a bit of a more mythologized conception and isn't a consequence of the cosmology, maybe isn't very plausible anyway. Could you talk a bit more about this? And some of the issues come up there.
Sure. I can start this, but obviously I think Phil can continue. But the story of Big Bang, in some sense, so it shouldn't be taken as a scientific statement that Big Bang, everything started with the Big Bang. I mean, of course, there's this sitcom Big Bang Theory that starts with that, but that doesn't. You don't always watch your sitcoms for the scientific accuracy. But the question, why do we say that? And I think there's certainly one line of thought that says that there was a beginning, and it's we kind of trace that back to the so-called singularity theorems, which are mathematical statements first proven by the famous late Stephen Hawking and Roger Penrose. Funnily enough, in fact, where I'm sitting right now, next door is where Stephen Hawking used to sit when he visited here at Perimeter Institute before he passed away. So these theorems, they are very powerful theorems, but they are mathematical theorems. And in physics, there's a difference between physics and mathematics. In physics, we discover things, but we don't prove things because, in fact, you're never sure about your assumptions, what is the right assumption. So if you have your precise mathematical assumptions, you could prove theorems, but that's what you do in mathematics. In physics, we're never sure about your assumptions. And here, there were basically specific assumptions that went into the proof of the singularity theorems. And these specific assumptions were reasonable, that basically theory of general relativity is a good theory, that we live in 3 space and 1 time dimension with rulers and clocks and can measure space and time, things like that. So they had reasonable assumptions, like gravity is attractive, for example. But there are assumptions that may fail. But if they don't fail, they proved that there is a point at which basically you cannot continue time anymore. The clock stops ticking, and they call this singularity. And based on that theorem, they said that there was a beginning of time. Now, does that mean that universe started at a singularity? No, it doesn't. It just means that you have these assumptions, and those assumptions say that you cannot use your theories beyond a point. But now, in fact, even the people who proved those theorems, Stephen, before he passed away, and Roger Penrose, neither of them actually believe in those assumptions. They think at least one of those assumptions, probably more, fail. And in fact, probably most of my colleagues, I'm pretty sure almost all of them, they think that those assumptions are not reliable. So was there a beginning? We don't know. So I think really the way to think about the Big Bang is that there's a point beyond which we don't understand the physics. And then what came before that, that's the subject to speculation. We need better set of rules and maybe better set of data to actually say what happened. And maybe one just quick word I can add is, it's kind of like waking up from a dream. That's what I like to think about it. That it's not that there was nothing before that. It's just we don't know. We don't really have a good way of knowing what came before. So that's really what it is. That if you wake up at some point and you cannot remember what were you dreaming about before, that doesn't mean that didn't exist before that, or you weren't dreaming. It's just that we cannot remember. And our collective investigation into what came before the Big Bang is just a work in progress.
Yeah. Sounds good. Did you want to add anything on that?
Well, I'll just add that, we did a survey of physicists at a large conference in Copenhagen, and we asked them what they think the term Big Bang means. And we asked them various controversial questions in physics. What do you think about fine tuning and dark matter and dark energy and blah, 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 blah. The only one that got a majority vote was that the Big Bang shouldn't be understood as describing a beginning of time. What the Big Bang really is a theory that says the universe was in a very hot, dense state 13.8 billion years ago. That we can be very confident of. What happened before the hot, dense state, that we can't be confident about that. We don't really know. And that's where the fun begins, because where you're at the edge of knowledge, that's where we come up with new ideas, and there's all sorts of fun fights and conflicts about which one is the most plausible. But that's our path to progress, is we come up with ideas and then we try and narrow them down and make observations that could confirm one or falsify the other. So really, the Big Bang is you could think of it as not the beginning of time, but as the end of our current confident knowledge. And what scientists are trying to do, and what we describe in the book, is attempts to push beyond that and see what's behind the curtain, as it were. And that's the next steps in the frontiers of early universe cosmology.
Yeah, that makes sense. Yeah, that seems like the right way to think about it, as far as I know, anyway. But I did want to ask, because, like, I don't know, sometimes people talk about the universe coming from absolute nothingness, as I said. And I think you talk about this a bit more in the third chapter. But like for me, and I recall 10, 15 years ago, like Lawrence Krauss had a book, The Universe from Nothing, and he faced a little bit of backlash about this. But like for me, when I think about nothing or absolute nothingness, well, I think of nothing either functioning as a noun, it's picking something out in some sense, or as a quantifier. The noun sense, I can't even make sense of. It's like you're treating nothing as something, and like, what are you saying? But the quantifier sense, if you're saying like there wasn't anything before the Big Bang, that's coherent to me, and that's maybe a possible model. But anyway, yeah, I don't know. Maybe you want to comment on that, either one of you, I suppose.
Well, I'll just say that there's a lot of confusion about this topic. So one is that, let's take statement one: the Big Bang tells us the universe came from nothing. That statement is false. Right? It doesn't tell us that at all. It just says it comes from a hot, dense state. Then we might ask, are there models where the universe came from nothing? And what would we mean by nothing? So one model is that it came from a vacuum fluctuation, but I think we can all agree that's not nothing. But that's where the confusion lies, because that's a model that was proposed by Ed Tryon in the early 70s. And but there was another idea proposed by Alex Vilenkin in the early 80s. And this is not a universe from a vacuum fluctuation. So when David Albert criticized Lawrence Krauss about this, I think he was maybe confused, because Vilenkin's idea is not a universe from a vacuum fluctuation. The idea is that space is treated quantum mechanically, so it fluctuates into existence from a state where there's no space. Now, you could ask still, is there still nothing there? And I think you could say, well, if this model is to be taken seriously, there'd have to be the laws of physics there. And I think Vilenkin accepts that. But I think when theologians talk about God creating either ex materia or ex nihilo, what they mean is not from pre-existing materials. So if this model's to be taken seriously, then there wouldn't be any sort of materials as we would know them, at least. The laws of physics would kind of have to be there without any universe to describe them. How you make sense of that, I'm not entirely sure. But it's helpful to distinguish those three sort of concepts. One, does a Big Bang say the universe came from nothing? No, it doesn't. Two, is there a model where it comes from a vacuum fluctuation? Yes, there is, but that's not nothing. Third, is there one where there's no vacuum? Yes, there is. Is that nothing? Maybe you could say it, but there's some things to unpack. That I think that's hopefully sums things up.
Yeah, good. I mean, even when the creation ex nihilo there, like I would understand that is, it's not like God took a bunch of nothingness and fashioned it into the universe. Rather, I would understand that in the quantifier sense of nothing, right? He made the universe, but it wasn't from anything. He didn't use anything to make it. He just made it, and that's like full stop. And maybe something like that is the case when we think about the universe from nothing, right? Or if you want to say, well, it came from something that's, well, maybe technically something, but almost nothing, if that makes any sense.
I just had a thought, actually, and let's run it by Niayesh. Let's just think about this. So there is a quantum gravity theory called causal sets, and we talk about this in the book. And the idea is that space is like made out of atoms, and the number of atoms is not conserved.
So just as the space-time is
space-time, sorry. Space-time is made of atoms. And the number of atoms is not conserved, so they grow as the universe expands. Now, so let's imagine this. Imagine there was one space-time atom, right? And then tomorrow there's two space-time atoms. Yep. Would everyone be okay with that? Does anyone see a big conceptual problem with that?
Who is everyone?
Both of you, Niayesh and Troy. right? We're all
I'm
happy
fine
with that.
so far, I think.
All right. So what if it goes from 0 to 1? Is that okay?
Sure. Yeah. I mean, I think you should be careful that you cannot even count the number of atoms at a time, because there is no time in this causal set. So basically, they're just atoms with causal connections. So that's one possibility for basically a fundamental quantum origin of space-time, that you don't really have time or space. You just have like points, like events in a space-time, and their causal connections. But there could be many ways of putting in the time across them. So there could be, I mean, in some sense, saying that there is a time that there is no atom, that doesn't make any sense, because I mean, the time doesn't exist. The only thing that exists are atoms. But then you could kind of draw your time in different ways, that there is one atom or two atoms or many atoms. But there could always be one, I think they call it originary. Like there is one atom that's to the past of all the other atoms of a space-time. And that could be the first, the God atom, if you want. And everything came from that. But I think that God doesn't, at least in this causal set theory that I'm familiar with, again, my friends here work on, the God doesn't have a lot of properties. It just exists. And it caused all the other atoms to come to be. Yeah, that's certainly possible.
Yeah, that's good. I was gonna be a little bit concerned about talking about it going from none to one. I mean, but anyway, we don't need to get focused.
Maybe I can just say a little bit about this, because I think there's this issue of nothing. I mean, I think people, religions can say whatever they want. I mean, I don't really know how much point there is into kind of making statements from religion very precise, because I'm not sure if they are very precise. But in terms of, whether there is a sense to which there is nothing or there is something, the point really is that we have certain things we're familiar with, like there's water, there's air, stuff we can describe on Earth. Now, plasma is not something that we usually see in our everyday life, at least maybe 100 years ago, certainly. Now, you see the sun, but it is, if in terms of things we can touch, that's not one of them. Now, is that not, is plasma nothing? Maybe 100 years ago, or maybe a few hundred years ago, people would have, it wasn't part of everyday things we could touch. But then our physics progressed, and then we understood that there are these new phases of matter. And now we know there is plasma, there are all sorts of other weird phases that exist, and we can describe them. So these new phases could still be there, the phases that we haven't really managed to categorize and catalog. And if we want to use our dictionary to describe that, there is nothing in our dictionary. So is that nothing? I think it's nothing for now, but if we can kind of extend our vocabulary over time, then it would be something probably when we understand things better. And I think that's the way I would think about it. It's nothing in the sense that there's nothing in our vocabulary to describe it now in our scientific vocabulary. But it could be something when we start to kind of expand our vocabulary and understand these new phases, new things that exist, when basically quantum mechanics and gravity both become important at the same time.
Yeah, fair enough. I think I want to say that's maybe nothing in a different sense. Just in the sense you described there, maybe we just don't have a category for it, or don't understand it, or have some description for it. But yeah. But I do want to move on. So in the second chapter, you focus on the multiverse, or really, there's a bunch of different multiverse theories that like we might talk about the many worlds of quantum mechanics, or internal inflation that could lead to a multiverse, string and M theory, and we can get multiverses out of, perhaps more. But yeah, so maybe we'll start with Niayesh, if you want to, maybe without getting too many specifics here on the views, how might these theories bear on, well, the Big Bang and our cosmic origins?
Good. So indeed, there are different ways that multiverse comes about. So I think Phil mentioned historically, was it atomists who thought about many universes existing? But in fact, in the 20th century, in modern physics, there have been many places that the idea of many parallel worlds or multiverses come about. In quantum mechanics, for example, when you make a measurement, the question is, okay, where does the probability come about there? And there's one point of view that maybe, in fact, you have many parallel histories at the same time. And then when you make a measurement, you kind of, you decide which one of these parallel histories or which class of them you end up with. And so that's one version of multiverse. Usually you don't think that these ones can communicate with each other, but yeah, I mean, that's in a probabilistic or stochastic way that does exist. But then at another version of multiverse is in a string theory, for example, there are many possible solutions to the equations. And we wanted, at some point, the hope was in a string theory, we could predict everything, like what is the mass of electron and charge of electron and proton, everything would come out. But it turned out that that hope is becoming fainter and fainter over time. So maybe there are many, many possibilities. And in terms of the space of all possibilities, so that's kind of they call it a landscape, but there are basically many possibilities there. And the way it comes out in cosmology is that there is this period known as inflation, which is in fact the most popular pre-Big Bang theory. So if you ask what came before the Big Bang, before the hot Big Bang phase, in fact, most cosmologists would tell you that it was a period of inflation. Now, funnily enough, the survey that Phil mentioned, when we polled the scientists were there, and there were some cosmologists and some astrophysicists from various disciplines, it was not the most popular. It was not more than 50%. I think it was probably the most popular, but it was like 30-something%. Yeah, it's 30-something% of the participants said that inflation was basically the most likely model of the early universe. But so what it is that the universe was basically expanding at a very, very rapid rate, like doubling its size every kind of tiny, tiny fraction of a second. And its size kind of increases by 30 orders of magnitude, probably much more than that, at least 30 orders of magnitude in a tiny, tiny fraction of a second. So this is known as a period of inflation and was, first proposed by Alan Guth. There were others also proposed it around the same time. And it could solve a bunch of problems in understanding the early universe. Why is the universe so uniform? Why there is structure on various scales that we could see? And it could, in fact, but what's amazingly successful about inflation is that it can kind of kill multiple birds with one stone, which is this rapid era of expansion can give us a universe which is more or less uniform on larger scales, that we see the cosmic microwave background is more or less uniform on larger scales. But at the same time, the tiny, tiny quantum fluctuations on this rapidly expanding background gives us tiny fluctuations that we see in the cosmic microwave background. And over time, it could actually grow due to gravity and give us galaxies, planets, and stars. Everything that we see could come out of the tiny quantum fluctuations in this early phase of the universe. But another byproduct, another prediction of almost all inflationary models is that inflation actually never ends, even though where we sit right now, that early rapid inflation has ended. But if you look at the vast universe as a whole, there are all these quantum fluctuations, even though they are tiny over larger scales, there are places that if it's these tiny fluctuations prevent inflation from ending. And because the universe in those places expand very fast, in fact, most of the volume of the universe is occupied by places that are eternally inflating. And then these tiny quantum fluctuations, basically, because this is a vast universe, an ever-expanding vast universe, can essentially give you everything as possible. All these various various states in landscape of string theory, all the things that are possible that can happen will happen in this vast landscape. And that's basically how early universe, in particular inflation in early universe, can give you a multiverse by this basically rapidly expanding space with basically infinitely many possible quantum fluctuations.
Yeah, very good. And then Phil, so different multiverse theories have been challenged in different ways. Of course, you could have like more specific concerns, like recovering the Born rule in many worlds or whatever. But just to focus on a couple of general concerns. First, someone might worry that, well, these multiverse theories, they're quite like ontologically extravagant, theoretically complex. You have to commit to maybe many or even infinitely many worlds. In string theory, what is like 10 to the 500, 10 to maybe more different possible solutions? That just seems like a big commitment to make. And then the second worry would be regarding testability. Like, how do we even confirm a theory? Like, some of these might be in principle untestable, or maybe even testable in very limited ways. Like people talk about cold spots or whatever. But anyway, yeah, I don't know if you want to comment on these concerns.
Yeah, I mean, there's lots of controversy about the multiverse, and there's it's such a fascinating topic in my opinion, because there's really, I think, good arguments for and against. So let's now, if I was to say what worries me the most is the ability to test this idea. I think the ontological extravagance, I think I'm less concerned about, because to me, it's like saying atoms is extravagant. Oh, there was a debate about atoms, and in fact, people were like, how can you believe in these invisible atoms? There would be so many of them. So I'm not as worried. I mean, I guess you could say it's simpler to believe one universe than in an infinity of them. Maybe you could say that, but I think I'm not too. If there's a mechanism to generate lots of universes, then I'm not worried that there's lots of universes. But what I am worried about is, can we test whether this mechanism exists? And what I think is that I think in principle it's possible, but I think it's not as the evidence is not as compelling as has been made out to be. I mean, the mechanism is inflation, right? So, and some people would say inflation's already been proven. And one of my quests was to say, well, hang on, I'm not sure it's as sure as you'll say it is, and there's alternatives to inflation. So to me, the exciting game is, well, what are the alternatives, and could we test those? Is there any way to sort of directly test, whether inflation happened? So I think this is something that could be done in the future, but I don't think it's as sure as we've been told. But nevertheless, I think in principle, what you're not going to look, just the fact that you can't look through a telescope and see another universe, I think doesn't mean that there's no way to test the multiverse hypothesis. I think the best hope is that what you would do is try and find the mechanism that's supposed to generate the multiverse. Of course, there's always doubt whether you've understood the mechanism right. So, and we have to have doubt about that. But so there are, like, most of the cosmologists I've interviewed that work on inflation think inflation generates a multiverse. But I will name one, Slava Mukhanov, who thinks it doesn't. So there's some doubt about that too. There's one big problem that I think doesn't get talked about enough. It's called the measure problem. And that is, like, how do you do probabilities if you have a multiverse? Because then, you've got an infinite set of things that can happen. Having said that, you could have a measure problem even in a single universe. So if you have a single universe and it exists forever, you could have a measure problem there as well. So these are all, so I would sort of rank, to me, the biggest problem is, can we find out if inflation happened? Are we sure that it generates a multiverse? This is in descending order now. Then a measure problem. And the last one I would say is the extravagance. That one I'm less bothered about, but the more important ones I think are, testability and measure problem and so on.
Yeah, very good. And then, we can get, like, I know some people try to talk about self-locating probabilities and other potential solutions to recovering the sort of probabilities even for different multiverse theories, but it gets complicated there, and we don't need to get into that. But
I've been with Matthew Adelstein about that, and they are fascinating questions, but that's not something we get. That's philosophical, probably too far away from our topic.
Yeah, I think Sean Carroll has some papers on that. He talked about that, this self-locating probabilities, and I remember David Wallace in his book thinks he has some solution. Maybe there's some other ones, although. Yeah, we don't need. I mean, just to sort of unpack a little bit, this measure problem is, how do you calculate the probabilities? And one way you can do it is, you want to know who's typical in the multiverse, right? So, and that will give you the measure over the infinite space, because it's not true to say you can't do probabilities with infinities. You can, but it's difficult. You have to know what the order of events is, or what the typical observer is in the multiverse. And there are proposals for how to do this, but none of them are like definitive or agreed upon, and so there are a lot of issues to unpack there. Right. Yeah, and also in the fourth chapter, you focus a little bit more on string theory and brane theory, and so Niayesh, could you talk a bit more about these theories, and to what extent are these alternatives to the Big Bang rather than, I don't know, maybe extensions or?
So it's actually it's a very good point that I mean, to what extent are the alternatives, and really, you could also think of it as kind of criticism of inflation, because inflation, what it does is that it kind of pushes the Big Bang story farther back, but it's an incomplete story because it doesn't tell you what was the beginning of inflation or what was happening at the beginning. Or, I mean, there is, I mean, of course, it could be that it was eternal and there was no beginning. It was just going on all along. But still, you wonder, okay, so still you wonder, like, what happens if I try to kind of do quantum mechanics and gravity together? I mean, we still know that the black holes, if they collapse, if a star collapses in a black hole, there would be a singularity or something weird happening in the middle of it. Because I mean, I don't know if inflation is happening. At least I don't think inflation is a way of saving singularity, saving you from singularity, and inside the black holes. And I mean, at the fundamental level, we have these two sets of rules: quantum mechanics and then general relativity, that are inconsistent. So even if you have a story which you're happy with using the rules that, I mean, we know right now, we know that those rules are inconsistent set of rules. So it means that your story cannot be completely coherent, right? So there's something missing from that story, even though, I mean, when we tell the story of inflation, it looks like it sounds coherent. There are small corrections, but those corrections fundamentally are there. And if you don't understand them, that means that maybe they kind of come back to bite you at some point. And like string theory is again in some sense similar to inflation. That's the most popular theory of the pre-Big Bang. String theory is the most popular way of uniting the rules of quantum mechanics and the rules of general relativity or rules of theory of gravity. So basically what comes out of that, and this kind of in fact, you could think of a string theory as a criticism of inflation if you want, which people don't usually think of it that way. But it basically tells you that if you open the door of uniting quantum mechanics and gravity, then entirely new possibilities open up. You would have possibly new extra dimensions. String theory, which is ever possible, a potential of uniting these two, tells you that there should be 6 extra dimensions that we don't see at least. There could be more. There could be new objects like these branes that basically, these are kind of objects like membranes that live in these extra dimensions. So there could be other dimensions out there. I don't see them because I'm kind of confined to these branes. And these objects could move around. They could interact, these branes, with each other. And of course, that's one possibility. If there's another theory of quantum gravity, then there could be other structures that are there. And then with all these different new structures, you could make very different types of cosmology that look very different from inflation. And I mean, inflation, what it does is that it thinks, okay, you have general relativity, quantum mechanics, they stay close to what we think they are. They all behave nicely, don't interact with each other very much, only kind of very, very weakly. And then everything is kind of like that. But we know that if you open the door to a new theory of quantum gravity, which almost everyone believes we do need, because we don't really have a theory of quantum general relativity, then there could be many, many new possibilities. And and that's kind of a blessing and a curse, because of course, that opens up the room for imagining many, many different things. We talked about a few of these possible models inspired by string theory in our book. There are at least a dozen of them. Well, half a dozen we probably cover in the book, but there are many more out there. There could be like fewer dimensions, more dimensions. There could be a gas of strings. There could be these branes that are smashed together, that the pyrotic universe that Phil mentioned, and others. But it's also a curse, because then, okay, so there with all these possibilities, I mean, how do we make progress, right? And it's kind of the issue that the same issue with the multiverse, right? That basically there are all these possibilities that are out there, I mean, the multiverse, they are physically separated from us, but then when you add quantum gravity, there are many different conceptual possibilities, and making progress just becomes harder. So this is why we really need basically a synergy between like theoretical progress and observational progress to hopefully pave a way to kind of a sharper view of the early universe.
Good. Yeah. And then in the fifth chapter, you look more at time and whether, well, there could be time before time in some sense. I wanted to start first, and Phil, maybe you could comment on this. One of the worries I have when thinking about time and the Big Bang, it's like maybe that our like everyday temporal notions, and maybe even those that we employ in our physical theories, it might be inadequate or inappropriate for thinking about what's happening at or before the Big Bang in these terms. Maybe in more ways than just, well, okay, maybe there is no time before the Big Bang in the same way there's nothing north of the North Pole. But it just might be that maybe these notions sort of break down or inapplicable or insufficient for theorizing here. I don't know if you see what I'm getting at, but I don't know. What do you think?
Yeah. Well, there's all kinds of ideas. So it's, yes, certainly conceivable. And certainly we do talk about models where time disappears at the Big Bang. And in fact, two that come to mind, I don't think they're in the fifth chapter, actually. So one is the Hartle-Hawking model, which, if I remember rightly, is chapter 3. And then there's holographic cosmology. So they're slightly different from each other, but they both have in common this disappearance of time. And so time would be emergent property of something more fundamental. And we're used to that in our everyday lives in the sense of, well, we know that water, is made out of atoms. The atoms, water is wet when it's in a liquid state. The atoms aren't wet, but when they come together in a certain way, you get this property of wetness. So we're used to the idea of emergence. I think it's getting more common now, but it does feel like time. Surely that's so fundamental. Like we can imagine like the wetness of water emerging from atoms that have no wetness. Very hard to picture a world with no time. But there are theories that I think we have to take very seriously. The Hartle-Hawking model here's a difference. So in the Hartle-Hawking model, it was proposed in 1983, I think, by Jim Hartle and Stephen Hawking. And what they tried to do was sort of model the Big Bang, but bring in principles from quantum mechanics. And what they found was that instead of having 3 space dimensions and 1 time dimension, you have 4 space dimensions and no time dimension. And this actually resolves the singularity. So there's no sort of single point of origin to the universe. So that's the Hartle-Hawking model. Now, the holographic idea is similar but different. So time is similar in that time disappears at the Big Bang, but rather than having 4 dimensions of space, you have 1 less dimension. So you just have 3 dimensions of space and no time. So you could also have a period of like a quantum gravity era, and then time comes back in on the other side of it. So our next chapter after string theory is about loop quantum gravity, which is a rival to string theory. And they have this bouncing model. So there's this sort of quantum gravity era. And then if you could move through the other side of it, you'd have just classical world again. So time would sort of come back in, as it were. So there's definitely very legitimate ideas that time disappears at the Big Bang. But we have to keep in mind that we don't know if they're correct, and others maintain it. So, I say keep open-minded. And the fact that you can't imagine it, well, I think we should learn from quantum mechanics that, look, at the fundamental level, the world is very strange. So should we really be surprised that the Big Bang is very strange? I don't think so.
Yeah, fair enough. And I do want to cover a few of the models that you go over in the book that we haven't really discussed yet. So one, okay, maybe we start with there's certain time symmetric models or time symmetric universes, and I just want to ask about this. This also raises a question to me about like beginnings, right? Because if you had a universe, so I think Sean Carroll and Jennifer Chen had a model along these lines where there's sort of an origin, in a sense, in the middle, and then the universe proceeds in both ways with the thermodynamic, the entropy increases. But is that right to call that middle point the beginning, or is it because in a sense there's time before it? It's just moving, the arrows going in the other direction. I don't know. Maybe if you want to talk a little bit about this sort of model and whether that really has a beginning, or what do you think about that, Niayesh?
Yeah, so it's I think it's kind of fair to call it the beginning, because if there's a point where from which basically time runs out in either direction, then that's the beginning of time, no matter which side you're on. But yeah, it is and yeah, it's a question of how do we express time? And this, I mean, one way to think about it is maybe I mean, there is a second law of thermodynamics, which is that the entropy always increases in time. And of course, I mean, entropy itself is an emergent property. Like for a single atom, it doesn't make sense to talk about entropy, or a single electron. It's just one state, one particle. So when we think about like lots of particles and like the complexity of the state that they occupy, we think about entropy. Now, could it be that time as well? I mean, as Phil was saying, if time is also an emergent property, so they're both really properties that that kind of you could only associate to complex systems, and then maybe entropy is really a measure of time, not rather than kind of we seeing the second law is not really telling us that entropy increases in time. It just actually defines time for us in some sense. So that's kind of one idea, and then you could imagine, okay, so maybe you had some chaotic universe, the chaotic history. There was just some point at which the entropy just happened to be very low. And then, and that point was the origin of time. And then it was a minimum of entropy, and then it would be larger going forward or backward or in either direction. And then you would think that as the origin of time. So, I mean, I think that seems plausible. Yeah, I mean, if you don't think time is a fundamental property, that certainly makes sense. That basically there would be, I mean, where you don't have this, where it's not emergent, or where it hasn't emerged yet, then you don't really have a notion of time. But then where it has emerged, then you kind of identify arrow of time with the arrow of entropy, if you want. So that's I think that seems plausible. Now, whether we can test this, that's of course a good question. And I think this general notion, it's very hard for me to think if you could just test that particular idea, but there are specific models that have this feature. For example, there is a model that my colleagues here, I guess they used to be my colleagues, they're now in Edinburgh, Neil Tuarak and Leighton Boyle, come up with, they call it a CPT symmetric universe, where basically universe is there is like a mirror symmetry at the time of the Big Bang. In fact, they want a singular Big Bang. Well, shouldn't call it a Big Bang, but there's a point of singularity. There's a point where kind of the size of the universe goes to zero, but then basically what came before was exactly what happens after with the reflection. Basically, the future and the past are exactly the same, but in opposite direction. And they have some ideas that, okay, so by studying the properties of the waves or particles, or usually the properties of the fields at that point where the future universe and the past universe, or the mirror universe, I think they call them, where they match each other, you could put some constraints on the kind of fluctuations you could have. So they think they could maybe explain, they have a model for dark matter that comes out of that as a type of neutrinos. They may have also some ideas for how the fluctuations come about. But yeah, so you can test this in the context of a specific models. But yeah, I think more generally, it's really hard to test this idea on its own.
I should just add that this name has been called the Janus universe. So the idea is that time runs forward in that direction and forward in that direction. So that's named after the Roman god of what is it? It's one looking in both directions of time. So exactly. And I have heard different people interpret it in different ways. So I know some people will say that middle point is the beginning and some don't. But I think everyone agrees what the maths is. And then there's a question of what you call it. But I don't think we should worry too much about what to call it. Everyone agrees on the sort of mathematics of the theorem. But what's important is that tell me if anyone thinks that I've got this wrong, but there's no creation ex nihilo, if that's what you mean by beginning, right? Then that doesn't happen. The universe exists for all times. There's no point where it's like doesn't. Well, you could say some models that might have zero volume. I think in the CPT symmetric universe, it does have zero volume. So, but nevertheless, it goes in both directions. But in other models, it wouldn't have zero volume. So it depends on the model, and how you interpret it.
Right. Yeah. And it would be sort of weird to say that there's sort of single direction of time that's like the way it is in our side of the universe, but for some reason it's going backwards earlier than that. So it seems sort of weird. But
embrace the weirdness. Embrace the weirdness.
Right. But then, I do want to cover one more sort of model. So the sort of black hole genesis models, what we might call them. I recall like Lee Smolin had a view along these lines, where there's sort of this black hole cosmic evolution sort of thing, where in a way we get the universe is sort of fine-tuned for black holes because there's more universes that are produced by them and so on. Although he also has this thing about how the parameters change a little bit or can vary a little bit, almost in the way you can have mutations in natural selection. But and Niayesh, you have your own version of this that you've developed, as I understand it. So I don't know, maybe you want to talk about this sort of model and where you've taken it.
Right. Yeah. So so actually, I guess there are two possibilities that you may make a new universe outside a black hole or inside a black hole. And I think Lee's model is you make a new universe inside a black hole, which is really cool because we have millions of black holes in our galaxies. There are millions of universes, so it's kind of like a multiverse, but they're all inside the black holes. So it's very accessible. You just have to jump into a black hole to see it. It's a small price to pay. But mine was a little bit, I think it's different. It was just basically a single black hole, but it was a higher dimensional black hole. So the idea was kind of when you think about, so there is this thing within black holes and Big Bang that they both have this quote unquote singularity, which I said is not really a thing, is a place where our laws break down. But nonetheless, if you take the laws of general relativity and push them inside a black hole or towards the Big Bang, and then push them far enough, then they hit a point where basically everything becomes infinite. And time stops ticking, basically. And the question is, okay, is there a connection between these two? And I think there's this curious, funny thing, though, that so you might have heard about white holes. So white hole is kind of like a black hole, but like reversed in time. So everything falls into a black hole, but everything falls out of the white hole. And the Big Bang singularity is more like a white hole because it's the past, not in the future. But in fact, what we know is there is no white hole. Well, if when you form a black hole from a star, there is really no white hole there. You just have a star that's collapsing into forming a black hole. So that was kind of the key idea that got me started on this. We said, okay, so what if the Big Bang singularity is like a white hole singularity, is more of a mirage? Because white hole singularity is, we keep pushing things back in time and we hit this singularity, but it's not really there. It's just a star that's collapsing and forming a black hole. So maybe there's something similar that's happening for the whole universe. Yeah. So the Big Bang was not really a Big Bang. It was maybe a collapsing star. But of course, the collapsing star is the center and as an edge. The universe doesn't seem to have a center and edge. Everything is uniform. So to make it work, I needed to add one extra dimension. So that was a small price to pay, but still the price to pay an extra dimension. But then that was the idea. So that basically instead of a Big Bang singularity, you had the collapsing star, and out of that, there was some process that birthed our expanding universe. And I think I like the idea. I think some things fit, but then there were other things that didn't fit. And at some point, in terms of comparing it to observations, with my students, there was Natasha Altamirano and Beth Gould. We kind of explored, and it looked like the places that were consistent with observations had theoretical problems, and that's kind of where things stand right now. That it's, I'm the one who is supposed to champion it, but also we are the ones who found the problems with it, and that's the nature of science.
Yeah, so I did want to ask. It's been roughly 100 years, maybe almost 100 years since it was discovered that the universe was expanding and the Big Bang theory, in a sense, was first developed. Phil, do you feel that we're now maybe on the cusp of a new cosmic revolution, or what do you think?
I hope so. I tend to be an optimistic person, so I think there's new discoveries happening all the time. I mean, of course, in 1998 we discovered the universe was accelerating its expansion. That is an incredibly exciting discovery. So that was very, very exciting. The book is very much about what might have come before the Big Bang. Inflation is sort of the leading candidate. And I think we talk about ideas where we might be able to sort of decide if inflation really happened or not. A lot of cosmologists think they've already decided, but we don't think it's quite settled yet. So there's lots of exciting projects that can probe the early universe. Recent discovery is tentative, so I don't want to maybe mislead people to think it's all confirmed yet. But a recent potential discovery is that the acceleration of the expansion of the universe is not driven by a cosmological constant. Most textbooks, there's this thing called the standard model of cosmology. Lambda CDM is called, and the lambda, the CDM is cold dark matter, and lambda is this thing called the cosmological constant. So a lot of people think this thing that's causing the acceleration of the universe is a constant over time. But recent evidence suggests that actually not a constant, it's changing over time, which would be incredibly exciting if we can confirm that. And there's been a group called DESI who have announced sort of 4.2 sigma discovery of a change. Now, we'd like it to get to 5, but also we want other teams to confirm it as well, because I never believe any one team, or at least, the fewer the teams that make this announcement, the less confident we should be. So we want to see if other teams confirm this. That's going to be incredibly exciting. And, what I think is the most exciting thing is that we've opened up just not less than 10 years ago, we opened up an entirely new form of astronomy, which is gravitational wave astronomy. And before, it's all done through light. I'm an amateur astronomer, and I take everything's done through light, photons falling on sensors. But now we've got, with gravitational waves, an entirely new way of probing the universe. And this is particularly relevant for our question, because our question is, what happened 13.8 billion years ago? And the bad news is there's this, cosmic microwave background, which is really the oldest light that you can see. Now, that's a very interesting probe of early universe cosmology, very exciting probe. And there's more we can do with it, looking at the polarization of the cosmic microwave background. There's much more we can do with CMB. But ultimately, it was emitted 380,000 years after the Big Bang. Wouldn't it be great to have something that was emitted, at the Big Bang? And gravitational waves have that potential. Unfortunately, what the universe gives with one hand, it takes away with the other, because the reason that it can go through, basically the universe is in like this thick fog of a plasma, very similar to like the sun, right? You look at the surface. In fact, I do amateur astronomy on the sun as well, and I take pictures of the sun. And of course, I only take pictures of the surface. But you can, through seismology, you can actually infer what's happening at the core of the sun. So the Big Bang is something very similar. You've got this dense fog of the plasma, and we can't see through it. But gravitational waves can travel through it. So that's great, right? So that's really good. But on the other hand, their ability to travel through it is caused because they interact so weakly with everything else, which means they're going to be very, very hard to detect. But we've just started on this gravitational wave astronomy journey. So in the future, the hope is that we could detect gravitational waves from the Big Bang, and that will give us enormous amounts of information, and that will be revolutionary.
Yeah, very, very good. Yeah, I mean, I've heard stories about the sort of detectors that people develop like underground in the Arctic, or like at 0.001 Kelvin, or like some crazy setups that it's to try to get something to interact with it, maybe gravitational waves or whatever. Or maybe I'm thinking of something else, but
yeah, you might be thinking of neutrinos.
Maybe
and stuff like that. So gravitational waves, the main way to go after those is through laser interferometers. So what you have are these long laser arms, and you look for disturbances, and they basically align and then when the length of the arm is stretched or compressed, then the laser waveform goes out of phase, and so that's telling you there's a gravitational wave coming through. Although Niayesh has worked on another way to detect gravitational waves with is it Bose-Einstein quantum state? Remind me.
Right. I mean, it's a proposal. It's somewhat futuristic, but that actually does involve cold atoms, and the idea is basically instead of laser, maybe you could use just cold particles that sit in special quantum states, and they would just still. I mean, if you could measure things precisely enough, then they could do the same thing that a laser does for you, because basically the idea is that the gravitational wave comes through and it kind of disturbs things a little bit. And that if you could basically, I think nowadays we are in the age of quantum kind of sensing. Everything is going to be done like very precisely, quantum technologies, because I mean, part of it is quantum computers is like motivation for this, that if you want to have quantum computers, you want to basically measure quantum processes very precisely. Otherwise, there's no advantage to using quantum computers. And these precision measurements of quantum kind of properties then can be used to sense like passage of gravitational waves in principle. Now, in practice, I think there's a lot of hurdles to be crossed, but I think that's one possibility. But speaking of whether we are on the cusp of great discovery, I think Phil covered the experimental angle. I'm going to cover the theoretical angle. I think we are on the cusp of a discovery, because I know someone is going to read this book. It will be maybe a high school student or maybe a college student, and they're going to be inspired to work on Big Bang and quantum gravity possibly, and they're going to come up with the right model to actually make sense of what was going on back there, and then everything fits together. So that's what I'm excited about. So I think we are on the cusp, and we don't know who that person is going to be, but yeah, that's going to happen very soon.
I love the optimism. I did want to ask, and both of you can answer this kind of quickly. Do you have a sort of favorite model, or do you think that it's pretty likely that the Big Bang wasn't the beginning, or I don't know, what do you think? We can start with Niayesh if you want, or Phil.
Phil, you go.
Right. I don't have a favorite model, like honestly, and I think the chance of any one model being right are not that high, but that doesn't mean the chances of one of them being right is not that high. So maybe we've already come up with it. It's one of the models we described. Maybe it's one to come. But I do have I'm going to just say I do have a soft spot for the time travel models. So I just think they are really fun to think about. And so we haven't mentioned that, but there's an idea that maybe time goes in a loop, and that would explain, where does everything come from? What came from before that, and you just go round and round in a circle. So I do have a soft spot for those. But honestly, I think the thing to do is to be open-minded, and nature should decide. Now, it is a little bit different from my perspective to Niayesh, because Niayesh is a working cosmologist. I just interview them. So I just have to decide, is this plausible enough for me to make a film about it or write about it? But, working cosmologists have to commit a lot more time, so they have to decide, is this plausible enough to, worthy of my time? But for those of us who are just sort of outside observers, I think better to be an explorer than a believer.
I mean, I actually agree with that. I think it's better to be an explorer than a believer. And I mean, that's certainly my approach, because I mean, that's what a scientist must be. But actually, I gave you already one answer that is like, I mean, different models is like different children. You might have a favorite, but you cannot speak it loud. But in fact, in the book, I do talk about one, which I guess is in chapter 8. This is speeds of light, where we talk about whether, in fact, the speed of light cannot be the ultimate limit of a speed, but you could actually go faster than the speed of light. And the reason that's, I mean, even though I have worked on lots of things, the reason that one strikes me as the most interesting one is it actually connects with many puzzles across physics, from quantum gravity to measurement problem to the Big Bang. And it kind of brings all of them together in a sense. And in that sense, that's what we want from physics, that we want to unify all our puzzles, or So there are puzzles across the spectrum in theoretical physics and in observational physics. And I think in that sense, I think whether the speed of light is a fundamental limit, or whether in fact, as you go to the quantum realm or near the Big Bang, that speed limit is relaxed. I think that's I have a soft spot for that, if you want.
Good. I do have to ask. Maybe Phil, you could take this one. How do you think this the stuff discussed here and in the book connects to issues in theology and maybe like the Kalam cosmological argument?
Right.
And maybe you could ask, does everything that begin to exist have a cause?
Well, yeah. So I think there's a couple of ways it interacts. I mean, we talk about this in the book. So one, is there a sort of religion within cosmology? Are people too dogmatic about believing one model or another? And we think we do highlight the dangers of that. Then, of course, there's the religion within cosmology, and that's we focus on the Kalam argument and a little bit on the fine-tuning argument. So I think what we can say is that anyone that says the Big Bang has proven the universe has a beginning, they're misleading you. Like, it hasn't proven that. It might be the beginning. I don't want to claim that the Big Bang wasn't the beginning. It may well turn out to be, but we just don't know that yet. So that's the dodgy part of the Kalam argument from cosmology perspective. Now, I actually should add that, okay, what if the universe did have a beginning? Does it require a cause? And there we also are critical of that, because, there are models where even if time disappears, do you still have causality? It's not really clear. Is causality fundamental? It might be an emergent property. So I don't see any reason to think that the universe must have a cause if it had a beginning. So I think neither of these things are very plausible to me. And I'd add that one of the things I find interesting is that when you ask a theologian like William Lane Craig, well, what about God? Doesn't God need a cause? And they say, no, God doesn't need a cause because God doesn't have a beginning. And only things that have a beginning need a cause. I'm like, well, you're not saying God's eternal into the past, are you? And they're like, no. God was timeless and then entered into time. So that's why God is beginningless, not because he existed eternally into the past. But now think about the models that we talked about, the Hartle-Hawking model, the holographic model. They also are in this similar sort of boat, aren't they? They're like, well, they were in a timeless state and then entered into time. So why would they need causes? Like, you can't have it both ways. So I think there's a sort of inconsistency there. And the other thing where some of these Big Bang models interact is with the fine-tuning argument, because there's sort of several different ways you can reply to fine-tuning. One, of course, you can just deny that there is a problem, and that's actually much more popular than people think it is. So we did a survey of physicists, and actually the single most popular answer to the fine-tuning problem was, they're just brute facts, or stroke needs no explanation, because they're not demanding either a multiverse or God. So that was the single most popular answer. The second most popular answer was the multiverse. And a lot of theologians will say, well, that's, there's just atheists coming up with that to get rid of the fine-tuning argument. But I think what we show is that that's not true. That comes from inflationary cosmology. So to the extent that you take inflationary cosmology seriously, then you should probably take the multiverse seriously, with some of the caveats that we mentioned earlier. But then there's this other idea of cosmological natural selection, which is, although it might sound similar to a multiverse, and in some sense it is similar because they both involve lots of universes, but there's a very profound difference, because in the standard multiverse reply to fine-tuning, you don't assume that our universe is typical. It could be very, very atypical. You just need one universe. But in the cosmological natural selection, we would be typical. Our life-emitting universe is typical. So you're not appealing to what's called anthropic selection, rather you're appealing to natural selection. And so again, I mentioned this to Francis Collins, and he's a very famous scientist. He was the head of the National Institute for Health and was a health advisor to 3 presidents, and he's a Christian, and he likes the fine-tuning argument, says it must be God, or either that or a multiverse. And I said, what about cosmological natural selection? And he went, oh, that's very speculative. And I'm like, well, okay, it is speculative. But what we point out in the book, is it may have connections to other quantum gravity models. It seems to have a connection to causal set theory. So, so yes, it is speculative, but it's not more speculative than an immaterial mind did all this, and that's the competition, for the fine-tuning argument. So, if I have to choose between the two, I'm going to choose cosmological natural selection. So these ideas interact with these sort of theological arguments, and they are relevant. And if you read the book, we will unpack this in a lot more detail.
Awesome. Yeah. So I think I'll kind of end the questions there, but it's been really great having you, Niayesh, and Phil, and for writing this book. Again, the title is Battle of the Big Bang: The Details of Our Cosmic Origins. I'll include links to where people can find it. But yeah, it's been so great having you and having getting a chance to ask you questions about it and having a great, thoughtful answers. It's been great.
Thanks a lot. It's been a pleasure to be on.
Thanks, Troy. This was fun.